Hello and welcome back to Counting Rocks, an introduction to combinatorics at CSU. Today we're going to be talking about matchings in graphs. A matching is just a subgraph consisting of one or more disconnected edges. So I've just chosen these two yellow edges here, the ones that I've made thick, and in this copy I've chosen these three edges around the side. And in each of these examples, the edges don't share any vertices with each other, so they're disconnected edges. If I had this edge and also that one, that would not be a matching. The reason it's called a matching is that we're matching some of the vertices with each other based on the edges that pair them together. For instance, in this graph, we think of these two vertices as matched with each other, and these two vertices as matched with each other. And here, the bottom two are matched, and these two sides are matched, and so on. Another problem in graph optimization is finding a maximum matching. Now, a maximal matching just means a matching in which no more edges can be added to the matching. So for instance, here's a maximal matching because I can't add this white edge or that edge to the matching to make it also yellow without having two edges that share a vertex. But a maximal matching is not always maximum. Maximum means as many edges as you possibly can fit by still making a matching. So for this path graph on 6 vertices, you can have a maximal matching with 2 edges, but a maximum matching has 3 edges, every other edge starting with the first one instead of starting with the second one. So that's a more efficient way of matching, and we've matched up more of the vertices. So the question in graph theory about matching is, how do you find a maximal matching? How do you find a maximum matching? What's the smallest size of the maximal matching? This kind of counting question. Here's a simple algorithm for finding a maximal matching, not necessarily the maximum. You can always find a maximal matching by just adding new edges until no edges can be added. So for instance, we can pick this yellow edge and then this one doesn't touch it. I can put this one down here and also this one at the end. That's a maximal matching. Is it maximum? Maybe not. So let's explore. So we can improve this matching using the augmenting path strategy. That's where you find a path that starts and ends at an unmatched vertex. So here in this example, let's start at this green vertex and follow this green and yellow path up to this green vertex. Both of these green vertices are not part of a yellow matched edge. And find such a path in which the edges alternate, green, then yellow, then green, then yellow, then green, so the edges are matched starting with the second one and alternating. You can actually flip in this path whether or not the edges are matched or unmatched, and that also forms a valid matching because all of these other vertices are already matched, and so when you rematch them the other way, they're not going to interfere with anything else in the rest of the graph. And we've gone from 2 matched edges to 3 matched edges in this green path, and we still have our other edges matched elsewhere in the graph that aren't disturbed. And so we've actually gone from a maximal matching to a maximum matching using the augmenting path strategy. A very important case of matching is in the case of bipartite graphs. And let's imagine the following scenario. You have a plate of 4 different cupcakes. They're cupcakes C1, C2, C3, C4. They're all different flavors. They're very different cupcakes. And there's 4 people, and they all have very specific preferences of what type of cupcakes they like. Let's draw an edge between each person and the type of cupcakes they are willing to eat. Person 2, for instance, only likes the type of cupcake that's C1. But person 1 is okay with either cupcake C2 or C3. Person 3 is okay with cupcakes C1, C2, or C4. And person 4 is happy with C2 or C4. Is there a way to match the people with the cupcakes so that everybody's happy? So a mathematician named Hall answered this question completely in terms of when can you always match people with the cupcakes that they want. So define the neighborhood of a set of vertices in a graph to be the set of all vertices adjacent to some vertex in that set. For instance, if we take the neighborhood of the set of P1 and P2, what's the neighborhood of person 1 and person 2? It's all the cupcakes they collectively like. So P1 likes C2 and C3, and P2 likes C1, so together they like C1, C2, and C3. So the neighborhood of the set P1 and P2 is C1, C2, and C3. Hall's theorem says that a bipartite graph has a matching covering the left set, so every left element is matched with something on the right, if and only if, for every subset of the left set, like P1 and P2, the neighborhood has size at least the size of S. So in other words, the neighborhood has to grow, or at least stay the same size as you go to the right, and it can't get smaller, otherwise you get stuck. But that's actually the if and only if condition, that's all you need. So here's an example of a matching when it does exist in the graph we were looking at. We had P2 connecting to cupcake 1, and P1 connecting to cupcake 3, and so on, and this is a perfect matching. But this graph, if we just modify the preferences slightly, all of a sudden it doesn't have a matching anymore. In particular, these 3 vertices have neighborhood just these two red vertices. These two red cupcakes are the only two that these three people collectively like. And so there's no way of matching the people with the cupcakes because you run into a problem here. You can't give two cupcakes out to three people who only prefer those two cupcakes from the three of them. So that's why Hall's theorem is necessary, and why it's efficient is also gone over in the book. So now you try, find a maximum matching in the graph below. And what's the smallest size of a maximal matching? See if you can find both. And that's all for today, and I'll see you next time.